we said before, I'm gonna be jumping between this one and a couple of pictures, guys. I want to show you. Okay, electrical service. Like I said, guys, electrical service starts with the service point, right? Service point. That's where you bring your conductors into the building. There's a couple of pictures you're gonna be looking at. There's service. There's a couple of things you have to understand as we go through. There's the service conductors, service entrance conductors, service point, overhead service drop, overhead service conductors, underground service conductors, and service laterals. All these terminology that I threw at you in terms of when it comes to service. Then you land them in a service disconnect, and from the service disconnect, you put a switch gear or a switchboard or a panel, and you feed all your feeders and branch circuits from there. You're going to see when you look at the picture, it's going to be very clear. So here's what I would like to achieve, guys, from this one. Install power transformers to meet the NEC requirement. We're also going to talk about power transformers. We talk more about transformers next quarter too, but today we'll talk about transformers. We did calculation, guys, for transformer sizing primary and secondary conductors and overcapacity device. That's what basically this is talking about, Article 450. Basic transformer connection. This is, we're not electricians, but it's really nice to know how to have an open delta, closed delta, center tap delta, and a couple of these configuration. I know I had a presentation where I explained to you the most common services that we use, which is center, the delta is one of them, and also center tab delta as well as Y. Different service types that you can get. We talked about these one, guys, that goes from the 480/277 into the 208 in the US, 208, 120. These are your Y, and then you get a couple of deltas is 480 and a 240 and sometimes 208 too. So these are the services that you can do. The reason why transformers there are very important to the service, because the transformer will decide the voltage level. That's why you always start with a transformer. Like I told you before, if you have your choice in a commercial building, if you have your choice, what voltage would you use? 480, 277, if you have your choice. Why? Higher voltage, more efficient equipment. What's the problem with this one? You can burn all your lights at 277. The only problem with having a service 480, 277, anybody knows why? We have another transformer to step it down to 208, 120 to get the receptacle. So a perfect power distribution system is start with the 480, right? 480, 277, step it down to 208, 120, feed the receptacles, and everything other than receptacles will be fed, including the lights, will be fed from 480, 277. That's the ideal one. Okay, now I can use 208 for everything, like we did for this project. So that's what you want to do. Understand definition of various components of service equipment. I'm going to throw at you, which is really nice, guys. There's a couple of pictures. You look at them. Service point, service conductor overhead, service conductor underground, service lateral, service drop, service entrance conductors. So all these terminology that I throw at you, a couple of things, we'll talk about them. Install service equipment correctly. This for us, since we're not electricians, so we're not going to carry the tools, you will specify where the service equipment is going to be located in the building. We'll talk about the rules for locating the service equipment. Connecting metering equipment. The second thing, of course, metering is a big deal. So are you going to be on the high metering, low metering? We'll talk about the metering connection and the rules. Ground fault. Ground fault is a big deal, guys. We'll talk about the rules of applying ground fault. This is not the GFCI. This is called ground fault protection for equipment. We'll talk about the rules for that one. We mentioned it before. We'll talk about this one. And the last thing is grounding system. Grounding system, the rules for grounding system, we'll touch on a couple of things about grounding system. Any comments, any questions? So if you know nothing about the power system, this chapter should get you at least close to 70% of what you need to know, really, from everything that we have done so far in one chapter. It's really nice. A couple of pictures, nice, good stuff. Any comments, guys, about this? So service and grounding, start with a transformer, that's a source of the service, into the service conductors and all the stuff between them, into the service panel, the disconnect and the grounding. So that's what we're gonna do. So the first point Let me just see if I can get the picture nicer. The first point, guys, you need to start when you have a service. Oops, I might have to get my emails out of the way. Okay, close here. All right, here's the let's see if I can get a service. I want to go directly into a service. Okay, here we go. Service point. And there's, okay, here you go. Here's where I would like to go. This is the single most important article that you guys are going to be looking at. Look at this. This picture summarizes the whole service business for you. Let's start from the left to the right. Utility electrical supply system. I don't know if you guys can see that one. This is under the exclusive control of your utility right here. So you have the primary disconnected fuse to the transformers. I'm going to assign voltages here. So here's your 13.8K. This side, let's just assume this is 480/277. Okay, so I got the service, right? I got a 13.8 on the primary side of a transformer, 480/277. The utility will own and operate this transformer. Own and operate this transformer. Can I have thumbs up, Chad? That's your source of power to your building. Who's going to decide 480/277? The engineers as well as the utilities. Typically, guys, like I said, if you have a building 15,000 square feet or higher, it makes a lot of sense to use 480/277. Lower than that, 28120 is good. So I decided to use 480/277 here. So that's my service. Then, I don't know if you guys can see that. The service drop if it's overhead or service lateral. This conductor coming in here to the meter, that conductor is called either service drop if it's above ground, or if it's underground, it's called service lateral. Right? That's it. Is it hard? But so that's service drop or service lateral. Then you go into the meter. This is my meter. So you get your meter in. This point right here, the meter, is called the service point. Can you guys see that one? This is my service point. From the meter, you enter, I'm going to use different colors, into the service entrance conductor. Can you guys see that? This little conductor here is called service conductor. Right? Everybody can see that, service conductor. And the last one, let's use a different color. What color I'm going to use? I'm going to use a blue. And the last one here, that could be considered a feeder. That could be considered a feeder. And of course, downstream, here will be branch circuits. B is for branch circuits. Everybody can see that? These branch circuits. I'll use a third color here. These are my branch circuits. If you don't understand the power system, this picture should give you a full understanding of the whole power system. I start with a transformer. Let's just say this one 500 kVA transformer, 13.8 on the primary side. I step it down to 480/277. I bring it all the way to a meter. Out of the meter, I take from the transformer to the meter. It's called service drop, just terminology that they use, or service lateral if you're underground. Cool. Okay, service lateral for underground, and then you land in a meter, so you can meter equipment. Then from the meter into the first disconnect, this is called service entrance conductor, because you took conductors, you enter the building, right? And then from that one down, it's called the feeder. Any comments, any questions about this? I will emphasize the point, guys. Where is your service point? Can you guys see where service point is? Sometimes it's at the meter, sometimes it depends where service point, typically either at the meter, at the top of the mast. Okay, who cares? Here's what who cares. Now, who operates what, when, and where? So you can see this is your service. Now, service lateral, the utility, the electrical utility typically owns and operates this section here. This is owns and operates by the electrical utilities. So Excel Energy, Brian's company, is going to come and put the transformer here. They're going to pull the service lateral, underground, or overhead. The contractor might put conduits for them, but they pull these conductors all the way to the meter. The contractor will put the meter here. They will terminate their lugs into one side of the meter. From the other side of the meter, Jeff, as you know, you take the service conductor all the way to your building. Can you guys see where the demarcation point? So this is owned and operates from the meter end, owned and operates by the electrical utilities. Right at the meter, this is the point of service where you pull your conductors. Right at the meter in this application. And the rest of it here, this part here, is owned and operated by the owner, the premises. Can you guys see where the demarcation point? Can you have thumbs up, Chad? We fully understand what is a service drop, a service lateral, what is a service point, what is a service equipment. This is a service. This one is called the service equipment. It will be, how am I going to do that? This is inside a panel. All this will be your main panel, right? All this will be your main panel. Your main panel. Any comments, any questions, guys? Let me draw the riser for you that we guys had. If you guys remember, just quick here, here's my transformer from Excel that we did. We came from underground, let me just say here, and we came from underground, you guys remember that? And we went to termination box, or CT box. Then we went all the way to the main auto transfer switch, right? In our building, we went to right in here to auto transfer switch. And from the auto transfer switch, we went into my main panel. I'm not showing the generator. I'm just showing the power. So based on what we did for our project, anybody can tell me, right? Okay, so where is the service point? Where's the service point? Service point is right here, because the utilities typically either they put a meter right here next to the termination box, or they put it on the building wire to here. So this termination box, guys, is equivalent to a meter in a bigger system. A meter up to 200 amp, Darren, up to 200 amp, they can bring the wires right into the meter. Higher than 200 amp, they start putting a CT cabinet, right, where they reduce the current because it's too high, so they don't burn the meters. That's what you do 99% of the time, commercial, industrial, that's what you're looking at. So you bring, so who's doing what? This guy right here is your service, this is your service lateral. Can you see that? That's owned and operated by Excel. The high voltage side is this side. Can you guys see that? Here's my high voltage side, transformer. This is service lateral because we're going underground, service lateral. If that was overhead, that would be right. That would be a service drop. Then this is the termination box. This will be then my service point right in here. My service point, here's my meter, CTs, and then this guy, anybody can tell me what this guy is? This is my service entrance conductors, to the meter. Any question, guys, how to tie what we did for our project to this picture? Any comments, any questions? This is the single most important thing when you start looking at a power system. You start with the transformer into the termination box. We're not showing it here because it's a simple system. And from the termination box into a meter, into an auto transfer switch or a panel. In this case, we use an auto transfer switch. So my disconnect has to be located right in here. Here's my main disconnect. This is my service entrance disconnect switch. My service entrance disconnect have to be located in the auto transfer switch here.
When you say termination box, you mean termination box in your cabinet?
Yes. Yep. Termination box with a CT cabinet. Absolutely. Absolutely. So they have a box with buses inside it. You terminate, the utilities bring their cables from one side. You bring a cable from the other side. They have a couple of CTs that they measure the current and take a voltage, and that will be your meter. M is right here, sitting here. Either on the termination box, or it could be sitting somewhere on the building. Any comments, any questions about this before we leave it? Any comments, any questions? One more time. You always start with the transformer primary into the secondary, owned and operated by utilities. The utility will give you a wire, a cable, a conduit with wires. This is called service drop if it's overhead, service lateral if it's underground, into a meter if it's 200 amp or less, or a termination box if it's higher than 200 amp. Can you guys see that? Higher than 200 amp termination box with a CT cabinet. And then you go from there into your building. That will be your service entrance conductors. The first box, the first panel that you land in is called the service entrance equipment. It doesn't matter if it's a panel on ATS. So here's, in this case, an ATS auto transfer switch. This is my service entrance equipment. My disconnect, a fuse disconnect or circuit breaker have to be located right into this panel, or in my case here, right in this panel, right? And then from there, I can go and feed my main panel. I go feed this becomes, in this case, this becomes a feeder actually, you know, because we're feeding outside that one, it becomes a feeder. Any comments, any questions? And then here's a feeder, and then the rest of these are my branch circuit. branch circuits, right? Any comments, any questions? Can I have a thumbs up, Chad? We fully understand this picture. So that's what this is. What this is basically, this chapter is all about. I can't emphasize, guys, the importance. I can't emphasize the importance of who owns what. If I want you to highlight one little thing, I want you to highlight this service point, this particular service point, the location of the service point. It could be a termination box, it could be the meter, or it could be the mast at the top of the mast if it's a residential or likely commercial building. That could become your service point. Any comments, any questions?
That's where ownership changes.
Thank you. That's the demarcation point. That's who owns what, when, and where, own and operate. So from this side end, this is owned and operated by the electrical utilities. From this side end, this is owned and operated by owner. Can I have a thumbs up for this? The demarcation point is start with the service point. Service point could be either the meter. Who decides the service point? The utilities. They decide where the service point is going to be. Examples. Meter, if it's 200 amp, if this is a 200 amp or less, a lot of time they have the meter. If it's higher than 200 amp, the meter changes into a termination box, a big box like this. CT cabinet. CT cabinet or termination box, that becomes your service point, right? That's another, if you're coming underground. If you're coming from overhead, guys, here's my building, and you have a pole coming in here, and here's your transformer, and you're bringing your power from here into a mast that's sitting right here, and here's my meter. So this is the residential one. Everybody can see that? The service point here, in this case, is this point, right at the top of the mast. This is the service point. So who owns what, when, and where? The utilities will own the service drop, the transformer. I, as an owner, will own the mast and the service conductor that's coming in here all the way through the meter. The utility own the meter, not a cabinet. We own the cabinet. And all the way into my panel, right? Remember that? Dwelling, that's typically what we do in dwelling. Any comments, any questions? Where the service point is? Here's a location for the service point. Here's another location. Here's the termination box is the third location. Sometimes way at the top of the pole, they give you a service point. But there's a couple of service points. The key point is you have to have the service point located. I need thumbs up, Chad. Cool? Okay. So that's basically what I wanted to explain from the whole chapter is really based on this. Okay. So that's my service point. Now look at this here. So we have utility electrical supply system. So we have two systems here. Okay, we have branch circuits, we have overhead service conductors. If overhead and underground service conductor, what's the difference between the two? Okay, so we have the service point. Where's this? Oh, look at this. This is really cool. This is where the service point is. Can you guys see the difference between them? Anybody can see the only difference between these two is what? Can you see what the difference between them? Where's the service point here? Here's my service point. Can you guys see that? Here's the service point. This is uncommon where they give you access to their transformer. Utilities don't like to do that, guys. So if it's the service, the service point will decide who owns what. Then if it's the service point is here, then you own the overhead conductors. Highly unlikely. Overhead service, it becomes overhead service conductors. So from this point on, owner. From here, utility. You can see that?
What about the meter?
The meter will be the meter will be owned by the utility, of course, but you own the cabinet. The meter itself will be owned by utilities, but you own the cabinet. Any question, guys, about the service? The difference between the service point. When you put the service point, it decides what is service conductors. So look at this. If you put the service point here, they introduce something called service conductors. These are where service drop. Can you guys see that? And Darren, if it doesn't ring a bell for you, you and Jeff, that's because it's in 2011. That's changed in 2011. They introduced service drop most of the time you don't have a service conductor. You have a service drop or service lateral. Now, if you do it this way, this conductor here becomes, they call it service conductor. You still own and operate though, based on the service point. And then this conductor becomes service entrance conductor, and this becomes a feeder. So they introduced that and there is no service lateral. There is no service lateral in this case, or service drop. Any comments, any questions? Any comments, any questions? Typically, guys, you will have a service drop or service lateral into a box, and then you have service conductors. Any comments, any questions? Any comments, any questions about this? So that's what I wanted to emphasize, that your system is, the most important thing is the service point that you have, the service point that you have. I'm going to draw one little thing here, guys, because this is probably the most important things. I'm going to draw that project that we did here. This is transformer. I'm going to draw the auto transfer switch. I'm going to draw my panel, my main panel. Okay. If you guys don't mind me coming from the transform, and I'm going to draw a box here. This is my termination box. I'm going to put a building here. Okay. You guys remember what we did? We came from here underground to the termination box, and then into this, and then from here into that, right? This is your riser that you did with Chad. Okay. Now, I want you guys to tell me, where is the service point in this case? Termination box. That's my service point. What's the name of this conductor? Who owns and operates this conductor here? The utilities. So they have to put their conduits and wires. Who owns and operates this conductor right here? This is the service entrance conductor. We own and operate. Where's my disconnect switch? My disconnect switch is located right in here. My 500 amp disconnect switch. This conductor here is called service entrance conductor. This conductor here is called service lateral. Now, can I get you to understand who owns from this point this way? Who owns and operates? Utilities. From this point this way, who owns and operates? Us. The reason why I do this one is much better than the picture that you have, guys, but similar though. Where's the service point? I want to put my service point for you right in here. My service point is right here. This is called service point. Who's going to buy and place this termination or CT cabinet? The electrical contractor. It's responsibility. This box is owned and operated by the electrical contractor. You buy it based on the utility standards. They have a standard for them. You put it in a pad, concrete pad. You drop this CT cabinet or termination box right there. Then the utilities will come from one side and put their cables, and then you come from the other side and you put your cables. Can they have thumbs up, Chad? We fully understand the responsibilities, especially our ECDM students. I know you guys know it, the electricians, but you guys understand fully the responsibility, who's doing what. This is a big deal. When you guys start taking off the projects for me in the spring, are you going to take off this wire here and conduit? No. Are you going to take this box off? Yes. Are you going to take this conduit and wire in here? Yes. And of course, everything inside the building. Okay. I need thumbs up, Chad. Cool. All right. So that's the second thing I'm going to emphasize here. This piece of equipment here is called service equipment. Service. This box, the auto transfer switch, is called service equipment. Now, Adam, my friend, in the service equipment, you have to have a service disconnect means. Did you guys see that? You have to have a service disconnect means. This is where my 500 amp disconnect switch was located. Everybody can see that? My 500 amp disconnect is located here. This is my 208/120 500 amp panel, right? You guys remember? That's you size it with me. This is called service equipment. Who cares? I'm going to come into who cares. Who cares? Because right in here, you have to bring the neutral and to bring the ground And who's my favorite student to pick on? What do you do to the ground and the neutral inside the service equipment? What do we do with them? Bond them. So you're going to come over here and bond them right in here. Okay, good. So that will be called main bonding jumper. And how many times you sized this one for me last quarter or this quarter? Many times. So you see when we bonded here? Okay, now who's my next favorite student to tell me? What do you do to the ground here? You have to ground. So we bond the neutral to the ground, but you have to provide a grounding electrode conductor, right? So you come over here. Can you guys see that point here? And you bring it to the ground. And this conductor is called grounding electrode conductor. Can I have thumbs up, Chad? Grounding electrode conductor. This is the single most important thing that happened at the service. Number one, the neutral and the ground are bonded together with a piece of wire that's called main bonding jumper. The ground bar is going to the ground through a wire that's called grounding electrode conductor. You gentlemen have sized these for me before. And the service entrance equipment have to have a disconnect sized appropriately based on the load. Can I have thumbs up, Chad? We understand how we brought the power from the transformer into the termination box, which is a service point, and inside the building, right, the service entrance equipment, we have to bond the neutral to the ground, take the ground to the mother of nature, and to the ground, take the ground bar to the ground and bond it, right? Any comments, any questions? If you understand that, that's 80% of this chapter. These two pictures, 80% of these chapters. Any comments, any questions? Any comments, any questions? The last thing I want to say, termination box or CT cabinet. When would you use CT cabinet? If the service more than 200 amp. Can you guys write yourself a note? If your service is more than 200 amp, then the utilities force you to put a termination box or a CT cabinet. Why? Because if you bring 400 amps into a meter, they might not have a meter that can handle a 400, definitely not a 1,000 amp. Say you have a service 1,000 amp, you want to bring it directly into the meter, you will burn the coils of the meter. So what they do is they take a CT cabinet, and from the CT cabinet, they take that 1,000 amp, convert it to 5 amps. You guys know what the CT cabinet does? The CT cabinet, if here's phase A, is a donut. They take, suppose that phase A had a 1,000 amp here. It will take 1,000 amp and bring it to the meter. It will be seen inside the meter though as 5 amps. So every 1,000 amp will be seen inside the meter as 5 amps. So your meter actually seeing 5 amps only, maximum. So who's my favorite to say, what if we were pulling half of this? If we were pulling, instead of 1,000 amp, we were pulling 500 amps. What do you think the 5 trips goes down to what? Thank you, 2.5. So 5 is a max. So that's why you see you have a CT cabinet, guys. You have a CT current transformer that take you 1,000 to 5, 2,000 to 5, 4,000 to 5, 200, 2,500 to 5. So the secondary is always what? In the US 5. In Europe, it's 1 amp. In the US 5, the secondary is always 5. The primary changes. I can have 600 to 5, 1,000 to 5, 1,600 to 5, 2,000 to 5, 2,500, 3,000, 4,000 to 5. Typically, the highest they can get is 4,000 to 5. The secondary is always 5. So you take these 5 amps, you dump them across the meter. You can't burn a meter with 5 amps, can you? And then, of course, the meter is going to have voltage coming to it too. So by having the voltage and the amps reduced, but the voltage, you can run them you can run them with 120 or 277. You can measure the kilowatt hour that you need to charge the customers for. Any comments, any questions about this? Any comments, any questions? Can I get you guys to understand this one? Because the rest of it is history, if you understand this picture. Cool? Thumbs up, Chad. Okay, so that's basically what the whole service and the whole deal is. So I want to be referring to this, guys, as I move on with my presentation, if you guys don't mind me. We'll talk about these in a second. Okay, let me see. Okay, so that's So now that you saw the whole picture, the chapter is talking about different parts of it. Transformers. Everybody knows where the transformer fits in this picture. Transformers. What do they do with the transformers? They step the voltage to a usable power. So like the 13.8 that I put one side, step it to 480. That's what their job is. Transformers are available in a couple of things. Basic, either liquid filled or dry. Typically, most of the stuff that you guys are dealing in a building are dry type transformers, but you can have liquid fill. Liquid fill, they have the windings immersed in non-toxic liquid. Anybody can just guess which one is the better transformer. Dry, better as in terms of being abused and used and give more power. The liquid or the dry? Liquid. Liquid. But who's dangerous? Liquid is dangerous. That's why we don't use them a lot in a commercial industrial building. That's why utilities, what the utilities guys, when you get a bigger transformers, they're all some type of mineral oil or other type of oil, because it cools the windings much better. So they put the windings inside some type of the windings, some type immersed in some type of a liquid. Cool. So if it's dry, this means the windings, transformers guys get hot when they convert power. So you need to either cool them, natural cooling, or if they're oil, the oil will help in cooling these windings. Can I have thumbs up, Chad? So what you guys are going to be dealing with typically, for the most part, dry type transformers. When they say 2500 kVA, that's dry type transformer. When Excel comes up with a 20 megavolt amp transformer, you are looking at a big fat oil-filled transformer, typically mineral oil in this case. Cool? Okay, so that's what the transformer, that's just the beginning of the service. Liquid filled. So what do they do for liquid? Liquid essentially insulate the high voltage winding from the low voltage windings and cool them really better. Dry type, here's where widely used, like we talked about the dry type, widely used. I think you can get them probably a 3 megavolt amp, even higher than that. I'm just getting out of memory for dry type. You can get them really big. You start getting into the 10 megavolt amp, and that's liquid type. Okay, higher weight. So widely used. Why? Because they're lighter and they're less dangerous too, because they don't have fluid that could ignite a certain temperature. Dry, also what they do for the cores guys are open to allow, they design them in a way, they have fins so the air can go through them and naturally cool them. What happens when you guys take a voltage the voltage that much, reduce it to a voltage that much, there's losses. Losses are heat. Core losses, they call them heat. What happens if you put heat inside a transformer? The coils can fail on you. So the most important thing for a transformer is to be able to cool them, naturally cooling them. So when you put your transformer in the building, Joe, you have to allow at least 2 to 3 feet behind the transformer. Can't remember, is it at least 2 feet behind the transformer and around the transformer, so the natural circulation of air to cool this transformer. You can't just go put it in a room and close it from all sides and give it 2 inches from each side. You have to allow natural circulation of air to cool the transformer. Cool? So who cares when you become a project manager? That's for you guys when you become project manager. You're going to place your transformer. Am I going to throw my transformer in a corner, locked behind it in a little cube here? No, you're going to allow ample amount of time, 2 to 3 feet around that transformer, so it can cool. Okay, here's a typical transformer, guys. This is called substation. This one is special design, called substation. I don't know how many of you guys will deal with substation. If you have a hospital, sport arenas, bigger government buildings, refineries, data centers, notoriously famous of using a substation. What is a unit substation? A unit substation, guys, they use a high voltage section. This is 13.8 kilovolt. A transformer, the primary is 13.8K, and the secondary could be typically 480 volt slash 277. So you have 3 sections. You have 1 section for the transformer, 1 for the distribution system, 1 for the high voltage. And then you bring your power from the utility right in here, from the utility. So you brought 13.8 to your building, and you can see that. You put the 13.8, this could be your disconnect. Can you guys see that? This could be your disconnect. So you have a service at 13.8. You're getting a service at 13.8. That's what typically happens. Instead of your service is 480, your service 13.8. Mayo, we did things like Mayo Clinic is a lot of places for Mayo Clinic guys. They use this. So disconnect is 13.8. Then, can you guys see about how they are bussed into a transformer in the same box? They're going in the same box to a transformer, dry type transformer typically, and then they're bussed, no cables. They're bussed into a switch gear that could be typically 4,000 amp or 2,000 amp. These are what typical application for these. It would be 2,000, 4,000 amp panel, a switchboard or switch gear on this side, all bussed together. What's the advantage of having a system like this? Remember that you're bringing 13.8 to your building, Mayo Clinic, got in the building, the 13th floor. They bring in, anybody been there, we brought the 13.8 feeder all the way to the 13th floor and then feed with a substation like this the whole floor of that building. Anybody can tell me what the voltage drop when you have 13.8? Almost zero when you bring 13 volts. So no voltage drop issues. That's why bigger buildings guys love that system. This is probably you're looking at only use of 10% for the most part. Bigger, very high, bigger projects. 10% use. Okay. I want to bring to your attention, guys, the grounding bar at the bottom here. Can you guys see that grounding bar here? Can you guys see how they brought the grounding bar here? And here's a conductor coming to the ground and grounding it. That's your grounding electrical conductor. When you came to the neutral, this is the primary side. There is no, the primary typically is delta. Can you guys see delta? The secondary typically is Y. So when you brought the Y, then you bring, here's the Y, you bond this one to the ground. Can you guys see how it's bonding to the ground here? You're bonding it to the ground. And the whole ground is going right here to Mother Earth. So you're bonding the neutral to the ground, right into the substation. Can I have thumbs up, Chad? We fully understand that unit. It's called unit substation. You can get them, we designed them in 48277 or 208/120 volt. Got in the building, we did tons of them. Very expensive, very dangerous, because now you have the transformer sitting right inside your building. Who owns what, when, and where? Where's your service point? Believe it or not, the service point would be, in this case, that here's your service point. This is service point. You know, Excel will come and drop the conductor right here. We're not showing the meters here. We're not showing the metering, but they typically, and they meter you, they put CTs here, and they put a meter to meter you here. So they put some CTs, high voltage meter, and they meter you right there. Any comments, any questions? Am I the only one who's excited? For the most part. Any comments, any questions, guys? Can you see how everything is bussed together? Really cool. What, delta Y? So this is the best application that you can get in the building. Very expensive, but a good, very good application. Very good application. Okay, substation. Transformers. When it comes to it, I'm going to give you a break in a second, guys. When it comes to the transformers, I want Jamie, my friend, to tell me, does these tables look familiar to you guys? I hope so. Table 450.3a and 3b. These are when we size the overcome protection device for transformers. Remember that? These two tables when we size the overcome protection device for the transformers. The transformer installation. When we have an overcome protection device, a fuse or circuit breaker on the primary and the secondary of the transformers, these are meant to protect the transformer. They are not meant to protect the conductors. Though, having said that, with the tab rules they do, when you have a tab rules, they do. But typically when you size these fuses, you're sizing them to protect your transformers on the primary side or secondary side. Any comments, guys? Any question? I'll show you this table in a second here. Any comments about protecting the transformer? This just talks about the fuses and the circuit breaker on the primary and the secondary of the transformer. And we sized a few of them when we did the calculation. This talks a little bit about transformer connection, change high voltage value into a lower value so the building can use it. There's a couple of connection methods. I'm going to run right through that. Single phase, you can get, you guys can look at this. We did this one in the residential. Here's one transformer they can get. We did it in the residential. It's called the 24123 wire, right? That's your residential used in the US a lot. And coming from center tab, shall be a grounded center tab transformer. I have a picture of this one. You're going to look at it in a second here. That's what we use in residential. Open delta, you have a three-phase. These are different services that you can get. Remember, these are different services. Service number one that you can use is single phase. Single phase dwelling, you're going to look at it in a second. Service number two that you can get, not commonly used, open delta. You have two transformers tied together to give you a three-phase system. So three-phase system, and single phase power use only two transformer, provide three-phase or three-phase and single phase power for the open delta of its center tab. When would you use it? Usually used where the strong probability that there will be an increase in the load, And you guys remember when they have how we derate an open delta? Did you do an open delta with Gary? We did it with me. Open delta. So when you have an open delta, let me see. When you have an open delta, let me see if we can get to the open deltas. Okay, here you go. So here's the most common transformer that you guys are going to encounter. Let's go here. Here's the most common transformer, right? It looks like this. It's center tab. Can you guys see the center tab is grounded, and you get X1, X3, X2, and you get your 24120. This is your 240/120 volt service. Dwelling only. We talked about this in this side. From this side, you get 70, in this case, line to line. Most likely, two lines that will get you 13.8, 12.47, 2400. What else? 4160. These are the most common voltages on this side. On the second side, the only common voltage is 12240. Who owns what, when, and where? This is all owned and operated by the utilities, the whole deal, and they give you three wires, the service conductors, right? Any comments, guys, about this service? We did it in the dwelling, not a whole lot to it. Open delta. The open delta, when we do the commercial stuff, here's a nice picture of an open delta. They have two transformers, so what are we missing? We're missing another transformer that should be sitting right here, guys, on the primary side. We're missing that one. See how they wire it? So this will be your phase A, phase B, and phase C coming in. And from this side, I will have my phase A, phase A, B, and C. And that will give you a 240 system. 240, three-phase. If you have a neutral, this is where the wild leg, remember that little point here? They're grounded to the ground. This is where you get you that wild leg between phase B in this case, right? Phase B and the ground. Any comments, guys, about this? Where would you use this? This suggests that in an area where there's a growth. The problem with this, I don't want to emphasize it too much. We as an engineer, we don't specify it, guys. We specify three-phase transformer, done. These are three single-phase or two single-phase to make a three-phase system. Any comments, any questions? When I was in your shoes years ago, it used to confuse the crap out of me, guys, the whole voltages. And a smarter guy explained it to me as if you have just say 10 kW worth of power. If you have a 10 kW worth of power, right? I can deliver the 10 kW worth of power for you guys using any voltage system. Think about it this way. The voltage is a delivery method. A car. I can carry these 10 kW to your building using an airplane, drive it, right? Or using a car, a bus, a train. All these different delivery methods are different voltages. Can I have thumbs up, Chad? We understand that voltages are different delivery methods. The power is still power. By the way, I can deliver 10 kW using DC to your building, DC voltage or AC voltage, single phase or three phase, any voltage system. The key point is the 10 kW. How do you deliver it? You choose the best delivery method for the application. This delivery method is good for utilities because it saves them one transformer here, right? And in the future, if the load growth, they go through another transformer, rewire the system, and off it goes. What's the problem with this? You have to derate this one to 80, what is it, 86% of the size. So if I have 100 kW here, 100 kW here, you have 200 kW, you multiply this by 0.86. That's how much juice you can get out of this. Why? Because if you don't do that, you will overwhelm, you will burn the coils. Because you're missing the third transformer. Any comments, guys? Any questions about this open delta? This one is called the open delta center tab. Open delta center tab, like this, right? Open delta center tab. So the windings are right here. Open delta center tab. Open delta center tab. Any comment, guys, about open delta center tab? Not commonly used. Utilities use it sparingly. And I will give you a break. I know it. The last one here, guys, is this is the utilities use this one all the time. This is primary, secondary. This is typical. So you have 3 transformers. Look how they're connected on the primary side as a delta. Can you guys see the delta here on the primary side? On the secondary side, they're connected as a 4-wire delta to 4-wire delta. 4-wire delta connected on the secondary. I see a 3-wire delta. Where's that 4-wire delta?
That's what I was wondering.
Yeah, where is that? So let's go, where's phase B? Let's go to one of these phases, phase C. Here's how it makes it a 4-wire. You come to this transformer, we'll make it. The what?
The 2 dots, the ones on the top, the 4-wire on the right.
Those orange dots.
Right, those going up.
X1 on top and X2
Yeah. X1, 2, X1, X2, X1, X2. No, we're talking about 4 wires Z's. How many wires coming out of the system? It says 4. To make it 4, this is a 3-wire. This is a delta-delta. If it's as it stands here, it's a delta-delta. So now if you want to go phase B is the wild leg, which one is, okay, C and A, you have to take this one here and take a wire from here, that will be my neutral, and then you have to take it down and to Mother Earth. There's a 4-wire system. So they take it, they ground the center of one transformer. Center of one transformer. Okay, so which one did we do? This one, right? So here's there will be a coil here. They take the center of that coil to the ground, and they pull a wire from here. That will be my neutral. You got yourself a 4-wire, right? A 4-wire will get you the neutral. Any comments, guys, about this? Any comments? Any questions? Any comments? Any questions? So that's that could be a delta-delta. This is common if it's 4-wire. Then in a case like this, guys, the primary here could be typically 13.8K, 12.47K, 4160 volt. The secondary almost always 240/120 volt 3-phase. You guys remember, this is the only way you can get 3-phase 240/120. The only way. From center tab delta. Center tab delta. You can also from open delta, it will give you, but still have either open delta center tab or delta center tab. Any comments, any questions about this? Should I give you guys 5 minutes? This is one of the most important chapters, guys. Summarize the whole power system in the building. It really is. So I'm just throwing a couple of pictures. I want to give you 5 minutes and we'll continue with it. The wild leg. Okay, so that's what I want to emphasize on that one. We talked about this, so I'm going to go get rid of the whole thing here. Get rid of my email so it doesn't keep popping up. The second thing I want to, and I'm choosing guys, bunch of these here. Does this ring a bell to you guys? This is 450.3a and 3b. What they did here in this sheet that you have in your book, they summarized table 450.3a and b, and I know, Darren, we used it last quarter. This is how we size a fuse or circuit breaker for the primary and the secondary. So I'm going to go over one thing. So if I have a transformer over 600 volt with a primary and secondary protection, so I have a fuse on both sides. If the impedance is less than, not more than 6, typical, then the primary overcomplication device, the maximum fuse 300, maximum breaker 600. If it's primary over 600, if it's secondary over 600, here's your multiplier, and if it's secondary, here's your multiplier. So they just arrange the table in a nice way. Can I have thumbs up, Chad? We know that. Really, this is the table, the two tables, 450.3a and B. They just arrange them in a really nice manner. That's it. So then if you have a circuit breakers, they arrange them in a different way as if you don't have a circuit breaker. Any comment, guys, about this table? I know we've used it, and I highlighted it for you guys when you were using it. So here we go. Look at this. This is if you have primary and secondary. This is if you don't have a secondary. Can you guys see that? No secondary fuse. Same thing, no secondary. And the same thing, secondary fuse, primary overcomplication device for high voltage. Any comments, any questions about this table? So I trust that you guys know how to use it based on the impedance, and we did a couple of questions about it. And guess what? We will be doing also too. So if you want to size the fuse, for example, to this, on the primary side, let's just say secondary over 600 volt, secondary over, so the secondary over 600 volt, here's your multiplier here, 300 for fuses. Let's say the secondary less than 600 volt, your multiplier for the fuse is 125 and the circuit breaker 125. And if you guys remember, I don't know where they put the note number 1 that you can go up. In the table, there is note number 1 underneath each one of them that allows you to go up if it's not a standard.
It's at the bottom of the table.
Is it at the bottom of the table?
Yeah.
Okay. Where percentage marked with, okay, here you go. Corresponding, okay, thank you. The next standard up. Okay, they have an asterisk here, right here. Instead of putting a number 1, they have an asterisk. Okay. Any comments about this table? Can I have thumbs up, Chad? We know how to use this table. Aaron, my friend, Andrew, you guys are good? Okay. So that's how you use the table to size a primary and secondary fuse for a conductor. We've used it in the past, so nothing new. We talked about this one, here's a situation very interesting, guys. Look at this. I have a transformer, primary, secondary, and you have to size, look how they size it. For the panel, I have the transformer is 50 kVA, 480. Can you guys see how they sized it? We're going to be doing an example like this next semester. The same example almost. 50 kW divided by 480 give you 60 amps. Continuous load for conductors, they size the conductor based on continuous load, 75 amp. The overcomplication device is 2.5 from the table, 150. Then they went into the secondary side, 208, give you 139. They size the conductor and the overcomplication device based 125. And here's what you came up with. Then they came up with a maximum 150 amp fuse in a 200 amp disconnect here, and 175 amp disconnect, 175 amp overcomplication device circuit breaker. So this is very typical how you size a receptacle transformer, right? So this is my receptacle panel. This is, in the US, we use a receptacle panel. This will be my main panel. I'm taking a feeder through the transformer. This will be 480 delta. This will be 208/120 volt. I promise you, gentlemen, we will be using this one. If you read this one and understand it now, very easy. Take the full load down of the transformer, multiply by 1.25, size the feeders on both sides. On the primary side, since we're using a fuse and since based on 250, you take 250 times the full load current on the primary, size the fuse, and on the secondary 1.25 you size the circuit breaker, and off it goes. Again, I will be using this in same example, a couple of examples, guys, in the in the industrial project. Cool. And then they have an equipment grounding conductor. Can you guys see that? Came and bond the two together. And they have a system bonding jumper here. Can you guys see that? I can't emphasize. Everybody can see the system bonding jumper. We know how to size this one. They have a grounding electrode conductor, and they have the supply side bonding jumper. This green one is called supply side bonding jumper. If you understand this, you will understand the equipment grounding conductor, the grounding electrode conductor. This is grounding electrode conductor. This is main, or in this case, it will be it's called system bonding jumper, and this one is supply side bonding jumper. All these are sized based on 250.66. This guy is sized based on 250.122. And you gentlemen have done these with me. And you will continue to do it when you do the calc. Any comments, any questions? I just throw this one to emphasize how important this sheet is, this particular graph. Okay? Any comments, any questions about this? Okay, so that's the calculation for this boy. And look at the color coding. I know this is very interesting, the color coding guys that they use, really nice color coding, right? So we have the brown, yellow, orange, which brown, yellow, orange, and we have the black, red, blue, and white. And if we have a gray, the gray will be going with the 480. Very nice. For years, Jeff, I've been using these books, and finally they said, "What do you need improvement, Chad?" I'm not kidding you. I don't know if they did it because I told them or not. Feedback from me said, "Color it," because that's my course books are all colored. I said, "Color it." Look how nice colored pictures gives you the color code for the system. They used to be just all one black wire. So I can't emphasize, these are very nice pictures, guys. Very nice pictures to understand the system. Okay, so we got that one. We got this symbol transformer, how they use it. We got this open delta. We got this delta delta, primary delta, secondary delta, 3-wire, and we made it 4-wire. This is a wrong one in this case. Okay, I think here's the 4-wire in the second one. You can see how the 4-wire 28120, you get it. 4-wire, guys. Delta. This is not a delta. This is the heck. 2828. Okay, what is that? It's a delta, right? Delta, let me see, delta. No, they're going phase A, phase B, phase C to the ground. Yep, this is not a delta, right? This is a Y. Scratch this one with the Y, will you? Right? Are you guys with me, right? Now Y, they take all the X's to one point here, and they tie it to the ground. That's a Y. Can you change that one to a Y? A Y. This is my Y. This will get you to 120. Okay, so that's what I'm going to say. I'm going to flip
It
here.
says at the bottom of that figure.
Is it Y?
It says 3-phase delta Y. So
Delta Y, but the graphic is wrong. Okay, not a biggie. We can give him a benefit of the doubt. Okay, so that's what I wanted to show, guys. A couple of things. We talked about this delta, open delta, 4-wire delta system. We showed you guys the 4-wire delta system, 3-wire delta, 3-phase 4-wire Y. 3-phase 4-wire Y, that's where you guys always going to be. 3-phase, they call it 3-phase 4-wire Y. That's where you're going to get your 480/277 and your 208/120 volt system. Jeff and Jamie, my friend, if you know these two systems, you are good up to 90% of the time. That's it. Everything else that I'm going to talk really is only 10%. Delta, delta, open delta, center tab delta, these are all the 10%. 99%, this is what you're going to be doing for commercial building and industrial. 3-phase permitted predicting. Why this is superior? Actually, I don't know. I've never seen this system. I don't know where you use this system. 460, 265. Darren, you guys seen that? 265, 460. This is the most common, of course, these two. Between these two, you covered 90% of your systems. Somebody research it, will you? Okay, so we got the Y. This is how you get it from the utility type. We as an engineer, guys, Aaron, my friend, when we ask for, we don't like this. We ask for 3-phase transformer. These are single phase, three single-phase transformers, right? Coming from the utility. When you have a commercial building, typically they don't give you a 3-phase transformers, typically, right? What they do is they give you a big fat transformer like this, right? And from here, that will be phase A, phase B, phase C, and from here will be phase A, phase B, and phase C, and a neutral. And this will be the transformer inside, say, 500 kVA. That's what you get from Excel. A pad-mounted transformer, typically for a building, 3-phase transformer. Can I have a thumbs up, Chad, that this is a 3-phase transformer? This is the rule, the exception is the single-phase transformers. If you have a little shop little strip mall, you'll see things like this. But if you have a commercial building, like any type of commercial building, you're looking at three-phase transformer. I need thumbs up, Chad, with that one. Okay, so that's my three-phase transformer. Primary connected delta for other connection qualified. Okay, we're good. Utility supply to the building are established by local. Okay, now who did what? The utilities guys that you have, the electrical company, decide the service point and sometimes the size, most of the time, the service point and the size of the transformer that they're going to give you and the voltage. The voltage, they're willing to negotiate the voltage with you, 280 to 120, but the size of a transformer and the service point and the size of conductor, service drop, they decide this. The service drop, service lateral, the size of the transformer, the type of the meter they put there, that's all electrical utility type work. Electrical utility. Okay, pad mounted transformer. This is the most common one that you guys are going to be encountering here. Pad mounted transformer. Liquid insulated as well as dry, typically dry that we use. Maybe fed from underground or overhead service. If you have a commercial building, typically they give you underground service like we did in our project. Secondary enters the building through a bus duct or a large conductor, typically through a large conductor, right? That's typical, guys, for a service, bringing it through a large conductor. So this is what we have in our commercial building. We have a pad mount transformer. We went underground with conduits and we fed feeders into that meter.
So the bus duct basically a bus.
Bus duct is manufactured, sandwiched in copper bars or aluminum bars in close proximity to each other, phase A, B, C, and a neutral, encased in metal, and brought to your building. It's like an extension of the panel. We use this, guys, typically if you service 2,000 amps and higher. That's a good application for it. Less than 2,000 amps, it becomes not good. You can use it, but not a good application. Expensive. Yeah.
It looks like 265, 460 is used for highway lighting a lot.
Oh, okay. Highway lighting.
Yeah.
Interesting.
Freeway lighting.
Yeah,
Wow.
that 460 is the most efficient. Like it carries the most. What was it saying? It was saying that
Yeah.
it uses the smallest wires or something like that.
Yeah, but why not 480? That's my question is. Why
Maybe it's
460?
Maybe it's the 265 that they're using
Yeah.
for the lighting.
Interesting.
So
Thank you,
the
Gush.
higher probably carry, like he's saying, because it has to go long distances.
Yeah.
So it carries the most energy with the smallest wires and starters.
Yeah, it's high.
Used for heavy industrial and large pump supply.
Okay. Yeah, but I was wondering if it's. I mean, I know utilities use 600 volt. They use 600 volt for lights, so they burn them at 600 volt. 600 volt go a long distance. So, cool, good one. We talked about unit substation, guys. That's the one when they bus all together, put the transformer, the high voltage, the transformer, and low voltage together in the same box. Require owner. It requires the owner to buy the equipment and maintain and troubleshoot it. So they have to have experience in the high voltage section. Here's what, let me guess, so utilities. Okay, here's a typical, guys, service. Please, guys, look at the picture, just the pictures. If you look at that one here, I have a primary service conductors coming in. That's owned and operated by the electrical utility here. Everything here is owned and operated by the electrical utility. Right in here, it becomes my CT cabinet. Can you guys see that? Primary service conductors. And then from here, this is my service point. Service point. Remember we talked about service point? And then service lateral or underground service conductor. In this case, or underground service conductor. So if this is a service point, then the owner will own these. If it's the service point is here, then the utility will own them. It depends where your service point. In this case, I put the service point right here, so all these cables right in here, owned and operated by the owner, and of course you have to have your disconnect. Can you guys see that? Main disconnect as you enter the building. Can I have thumbs up, Chad, for that one? This is also typical, coming from an overhead system all the way down to the primary side. So who owns what, when, and where? The owner will own this part, and the utility will own typically the transformer and this part. There's a CT cabinet with the transformer to the side of the transformer. Also typical. Instead of having the CT cabinet separate, they have a part of the transformer in a different enclosure attached to the transformer. Cool? So that's one application.
Seals are required.
Seals. Yeah, you have to see as you you have to have some type of duct seals so the water can't be channeled into. As you enter the building, you're required to seal the conduits right in here so it doesn't become a water channel the water into the building. Duct seal. Okay. All right, so that's your the other thing I want to show here, Aaron, can you guys see the disconnect? The disconnect is required to be as close to the point of entering the building as possible. I think was it in Wisconsin, 8 feet? You can't put it less than 8 feet. Very important. When you bring your service, if I want to bring my service from this wall, my equipment have to be on this wall. If I have to put my service equipment on this wall, I have to have a reason for putting it there. Otherwise, it wouldn't be approved. Everybody understand? Service disconnect have to be as close to the point of entering the building as possible for safety. So that's my conductors. Pad-mounted transformers. We talked about pad-mounted transformers. Here's what they're talking about pad-mounted. Here's what you're looking at, a pad and a transformer at the top of it. That's called pad. This is typical for all the projects that you're going to be doing. Pad-mounted transformers. Can you guys see that? Everybody can see that? Pad-mounted transformers. Enclosed weatherproof cabinets, well adapted to smaller service equipment, underground vaults. Sometimes they put them in underground vaults. If you go downtown Minneapolis, you don't see pad-mounted transformers all over, do you? When you move around, they're all underground, in vaults, underground in the vaults. Vaults underground, guys, is downtown cities, major cities. Downtown Rochester, Duluth, Minneapolis, St. Paul. I don't think Bloomington, we don't have a downtown. But downtown major cities, it's all vaults underground. Meter may be at the utility pole or inside the building. They either put the utility pole. A lot of people don't even put the utility pole anymore. They put them on the outside or inside of the building when you meter. Outside or inside of the building. Two ways of metering. The primary high voltage metering. This is when you guys remember that high voltage coming to the building. You put your meter right at the high voltage. So the commercial, okay, tenants, blah, 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 high voltage. Then you have to have a potential transformer, a current transformer to transfer the voltage to the meter. That's the high voltage section. The low voltage is you guys were going to be involved in. Most likely is the low voltage. Here's how the low voltage is. If you have greater, so low voltage metering of loads greater than this amount is accomplished in the same manner as high voltage meter. So you have a CET. If up to 200 amps, typically you can bring it directly to the meter socket. You bring the feeders directly to the meter socket. If you have multiple occupancy, what do you do for multiple occupancy? You have multiple meters for the multiple occupancy. Every occupant will have his own meter. Any comments, any questions? 200 amps, you bring a socket. More than 200 amps, you have CT cabinet, and you have the socket, the meter socket, away from you don't bring the cables to the meter socket, the power cables. Any comments, guys, about low voltage? When you say low voltage metering, we are dealing with 600 volt or less. Everybody understand? That's what low voltage metering, 600 volt or less. Okay, so we got that one. Okay, I'm not going to talk about these. I explained them, guys, a lot. Service drop. Remember that service drop that we talked about? Here's your service drop. Here's service lateral, service entrance conductors, overhead systems, service drops. All these, we explained them a minute ago. Service entrance conductors underground that they introduced. It's between the terminal equipment and the lateral. For all these terminologies, please look at the picture. The picture was much better than anything you can. Service lateral, that's when you come from underground. Service point, the most important point, as the point connection between the facility of the service utility and the premises. That's the demarcation point. It depends where. Sometimes it's the meter, pad-mounted transformer, CT cabinets, the top of the pole. Okay, so we talked about this one too. Service point, service entrance equipment. This is what service entrance equipment is. Consists of the following: the conductors, the main switch, or switches, the metering equipment, and the secondary distribution secondary distribution switches. These are called service equipment. The code, Jeff, defines the service equipment as where the service disconnect is located, the first panel, if any. If you have an ATS, auto transfer switch, that's your service equipment. You have the disconnect right inside the ATS, okay? Service. We talked about services, guys. Pad mounted transformers located outside the building. This is just for the project that they have. They have PVC conduit that runs underground service, bring the service from the pad mount transformers inside the building. Typical. You guys did that. You put a transformer outside into a pad mounted CT cabinet. From the CT cabinet, you went inside the building. Any comments, any questions? Gentlemen, there's a lot of people who would love to use you as drafters for the rest of your lives. What you see right now here is going to elevate your knowledge from being a drafter into being a designer. A designer will fully understand how you put the system together. What's the best practices for bringing a system? That's what this chapter is all about. Okay, understanding how the system is put together. Okay, here's here's how the building that we have. This is for the project inside your building, guys. They brought the service conductors into a gutter. Because these are multi-tenant building, the building that they have in this project is not single tenant, it's multi-tenant. Typically what they do, guys, is they bring the phases here and they meter them, right? And then they disconnect them. Can you guys see the disconnect here? Everyone is metered, disconnect, and this one is metered, disconnect. This is metered and disconnect and metered and disconnect all the way, right? The only one, this one have a CTs that actually went inside here, and then the power continued right through it to the disconnect and went in. Did you guys see the only difference here? Because that was, I can't remember what was it. That was more than 200 amp. One more time. All the rest of them are 200 amp or less, so we have a meter directly. This one was more than 200 amp, so we have to have a CT cabinet for it. Can I have thumbs up, Chad? That's it. You guys up and running. So where would you use a system like this? A strip mall, multi-tenant. So where's how many disconnect? What's the disconnect tool? 6 disconnect tools. Do I have more than 6 disconnect grouped together? No. 1, 2, 3, 4, 5, 6. So if I'm to shut down the power from this section of the building, the code says you can't have more than 6 disconnect. Now, Joe, what if I have another tenant here? Here's my meter, and I'm going to go all the way here. What do I do now? Okay, what do? You have a 7th one. Solution. Solution, gentlemen. You're gonna say no, we can't get you in here. They're paying money for you. Thank you. You just have a main disconnect here. So you grab a main disconnect and you put it right in here. That's all. Then you can have as many disconnects as you want. Okay? Very, very important. You can't tell the tenants you can't come here because the NEC code book said that you cannot. We are in the business of solving problems, guys. You have a problem like this, add another disconnect, main disconnect for the whole building. Any comments, any questions? That's the 6 disconnect tools. Yes, sir.
So you were saying earlier that when you have panel, high current panel or whatever, you have to have a CT to step it down to 5 amps. Well, if you don't have to have a CT, then is the meter built for handling like 200 amps or something like that?
200 amp or less.
Okay.
I think they make higher than that, but typically 200 amp or less.
Okay, so those meters don't have to be.
They don't have to be, they're rated to. You go higher than that, then you're doomed. It's not doomed, you have to have a CT cabinet. You have to have a CT cabinet if you go higher than that. For example, the bakery, this guy was 300 amp. This is a 300 amp fuse with a 400 amp disconnect. So what they did, guys, let me just summarize how it goes. So here's my CT cabinet. Inside it, I have a 300 amp, and the 300 amp will come from this side of the meter and will be seen as 5 amps. That's what a CT cabinet. Take a 300, they call it 300 to 5. So every 300 amp will be seen as a 5 amps. Can I have thumbs up, Chad? Okay, now half of this will be what? 150. What do you guys think? If it's 150 going through, what do you think this will be? 2.5. Does that make sense? Ratio.
So one of the owner sheet is saying you have to add that in, and it makes you need more than 200 amps?
That's when they're gonna ask you, say, well, I have a new tenant here, can you solve the problem for us? That's when you show your interest and knowledge in the code. He said, well, you can't, guys. You have to have a main here. And you know how much it costs you to cut through this gutter and put a main here? It's gonna cost you, it's doable. Everything is doable. We are in the business of providing solutions to the customers. So you can't go cut these conduits here and land them in a main disconnect here, right? And then continue.
How is the smart saying one of them ended up being more than 200 amps?
They want to change. Then you have to go check, do you have enough juice here? Okay, so this guy is right now 200 amp. He wants to go to 400 amp, right? Now, even the case, no problem. We get you an arrangement like this here. No problem. We take this out, but no arrangement. But here's before you do that. Do we have enough juice here to feed the extra stuff? That's why they hire you to analyze the system. So they hire an engineer like yourselves, guys. Go do a load study on that. So what they do is put meters. They will put meters everywhere. So make sure for a certain amount of time, and they get the bills from Excel Energy, and they look at the consumption of power here, and they say, do they really consume all this energy that's coming out of these conductors? If not, then you can add in, you're done. If they do, then you have to go change what? Yeah, but you have to just change that, because these feeders you might overload these feeders. Any comments, any questions? Because remember, Aaron, these feeders are based on what? The load calculation for the building. The load grows, these feeders might grow. Okay. All right, so that's a couple of calculations here. Service entrance conductor, we talked about these one, guys. They're underground service conductor, underground service conductors in the termination box. Service disconnect means, we say the service disconnect means have to be the first equipment the conductors will land in. Amp rating, you have to have, basically what they do is either a fuse, disconnect like this, or you have a circuit breaker. These two are called service disconnect means. If you have a breaker, you can disconnect and protect the system. If you have a disconnect like this, you can disconnect with this and protect with the fuse. So these two boys are equivalent to a circuit breaker. Can I have thumbs up, Chad? Okay. So we got that one. Service entrance conductor. How do you size service entrance conductor? I hope you guys know better than anybody else. Because remember that article here? Right? We did it exactly based on this article. You guys have done it for the 500 amp panel for me. Optional service electrical boiler. Electrical boilers, if you bring a service for them, you treat them as a continuous load and size it based on that one. 120. You take the boiler, because the boilers are electrical boilers are so huge, guys. You take the amp of the boiler, increase 25% for its safety, and size the service as a direct service to it. That's what they're saying here. Grounding and bonding. Okay, the system has to be grounded. I showed you guys how you ground the system by getting a Y, right? And you have to bond the neutral and the ground at the service, and you have to take the ground at the service and take it to Mother Earth through grounding interconductor. That's all in Article 250. That's all in Article 250. Any comments, any questions? Any comments, any questions? Grounded system. Commercial building love grounded system. When you say grounded system, guys, you're talking about 480/277 or 208/120 volt. These are the two systems that are commonly used, right? Grounded system. Ungrounded system, it's not commonly used. Okay, grounded. Common interest, preventing electrical shocks. Why do we do grounding? Prevent electrical shocks and stabilize the system and so forth. We'll talk about grounding in the industrial project a lot too, guys. Okay, now there are two types of grounding. Grounding the system, that's just to get 480/277, 208/120, and grounding the equipment. Grounding the equipment, guys, to protect you. Grounding the system to get you the two voltages. Can I have thumbs up, Chad? With grounding the system is to get you 480/277, 208/120. Grounding the equipment is to protect you. So if the phase is to touch the frame of a piece of equipment, if it's not grounded, it's waiting for you to grab into this hot and electrocute you. Everybody understand the difference? Grounding the system, it's called grounding electrode system. Grounding electrode system. Grounding the equipment is called equipment grounding conductor. So that's what all these talking about. Ground is connected to the Mother Earth. Uh, what does a fault current fault? This is just analyzing, guys. If you have a ground fault, the current goes right through the you and through the equipment and all the paths. Electrical fault. When we have electricity flow in every path. So if you have a ground fault, anything metallic between 2 points, they will be carrying that ground fault. So they have to be bonded together. I'll talk about this bonding. When we bond things, guys, you have two pieces of equipment right here, one piece here, and one piece right here. Why do you bond them together? Because you want them, and then you ground them. This is bonding because you don't want one of them to be at 0 and the other one at 480. So Chad grabs on this tank, put his hand on this tank, and the other hand on the panel accidentally. And guess what? The panel was hot, and the tank is grounded. So I'm sitting at 480 right across my heart, or a 277. That's how we bond them together. The whole bonding is to put them at the same potential. They call it the same potential. Shock hazard. The problem of a lot of shock hazard, guys, the reason why we do the bonding is to put them at the same potential, have low impedance to the ground to facilitate the operation of the grounding electrode system. The code requires the following. Grounding electrode system. If alternating current over 50 volt to this amount have to be grounded with some exception. So if you have a system higher than 50 volt up to 1000 volt, you have to ground it. 480, 377, 28, 120, 240, 120, with some exception. We'll talk about the different ways of grounding, guys. This is grounding ring. They put 20 feet with 3-aught conductor, beer cover around the building. That will be like a ground rod for you. And there's a bunch of requirements in these pages that talk about grounding equipment. It all talks, guys, about two things. Grounding electrode system, tying the service to the ground through a ground rod, a water pipe, ground ring, wire around the buildings. These are the systems. An equipment grounding conductor, tying the equipment together through an EMT conduit, rigid, right? Or through a wire. One of them is called equipment grounding conductor, size 250-122. The other one is grounding electrode conductor, size 250.66. Okay, sizing the grounding electrode conductor, speaking of the devil, you guys have done that, and I trust that you know it, and we will be doing it again using 250.66. And this is just saying, if you parallel sets, you guys have done this with me. If you have 3 sets of 500, what do you do with them? You multiply them by each other, and then you go to the service to 250.66, and you're going to find that for this service, the grounding electrode conductor is actually 3-aught. This concept is ground fault protection for equipment. Ground fault protection for equipment. This is very important, guys. If you write yourself a note, if you have 1000 amp or more, and if your system is 480 volt, 277 volt, then here's my panel. Look at this panel. I have 1000 amp or more, 480, 277 panel. If I have a panel like this, you have to have a ground fault protection. What the ground fault protection, guys, does, if the amp is so high, Jamie, a ground fault will be seen as a load, so it will not trip. It wouldn't trip. The main circuit breaker here, the 1000 amp, will not trip on a ground fault. So the ground fault sits there, arc until it creates a fire in your building. So the smarter than Chad, they create a little device here. It's called ground fault protection equipment, and they make it sense just the ground. It's looking at the ground, and if it sees a ground fault, it will trip. Just the ground, not the short circuit. Where is this required? It's like GFCI, similar. Where is it required? Here's where it's required. We have a couple of examples for it. So, because at that current, it doesn't... Okay, the last thing, guys, is OSHA, and you guys are not electricians, but OSHA will require you to work on energized equipment. You de-energize, you work on it, right, Jeff? De-energize work, lockout, tagout procedures. That's the requirement. If you're a project manager and somebody's going to go over the panel, We almost killed an apprentice here in Dunwoody because of that panel. With working at the Mall of America, almost burned his face. You know what I mean? So when you work on energized equipment, guys, the rule is the energized equipment, lock it, tag it. Only qualified people are working on it, right? And then you work on it. If you are to work energized, they have a work permit that you have to fill. Almost 6 people have to sign that work permit, all the managers. Make sure that you exhausted every option of working on this piece of equipment de-energized before you start working on energized. And then you put your personal protective gear rated based on arc flash, and then you start working on it. So all these are requirements so you don't kill electricians. Ground fault protection does not provide protection for personnel. That's from shock and so forth. This is not GFCI. Okay, so that's what I want to show you guys. I have a couple of pictures very quick here. I know my time is almost up with you. Okay, somebody asked about the bus. Okay, let's go here. Who asked about the bus? Here's a bus, a way of bringing the service to the building through a busway. Can you guys see that? Here's the transformers. We're busing them all the way to the current transformer. This is CT cabinet. Here's my disconnect switch here, and then this is my switch gear. That's one way of doing business, right? Here's another way of doing business. You bring your primary conductor all the way to a substation. Can you guys see the substation, how it's looking? High voltage section, current transformers are here, transformers sitting here, meter switch, a main switch, that main disconnect switch here, and your secondary switch gear. That's your unit substation. Any question, guys, about the unit substation? In this case, who owns what, when, and where? The utility, the demarcation point will be sitting right in here in the high voltage switch. Right in the high voltage switch. Can I have thumbs up, Chad, for that one? Okay. This is the example that we looked at, guys. This is what we have in our building. We're bringing to a transformer with a CT cabinet out into the building with disconnect. We looked at this. If you're downtown Minneapolis, this is what you get. You get a volt transformer inside the vault, and the same thing, you bring it to the basement to the building, and you power your building. Can I have thumbs up, Chad? That's how you do it in downtowns and all this good stuff. Meters, really interesting. Here's what you have in your house and mine, Jamie. This is called a 4-terminal meter. Can you guys see 1, 2, 3, 4? Typically dwelling 208, 120, up to 200 amp. This one is 7 meter sockets, 7 terminal. Why 7? 1, 2, 3, 4, 5, 6, the 3-phase, and 1 for the neutral, to sense the neutral. Can you guys see that? That's your 7. The last one, this gets you up 200 amp. This, they say, this is, I think this guy has a CT in it. CTs in it. So they split the phases into 3. Here's 1, 2, 3. Each phase is split into 3. Can you guys see that? I think a 3 here, or 2. 1, 2, 1, 2, and a neutral. So they have 13 terminals. You can use it on 3-phase up to 200 to 800. I believe they have a CT inside these jars, CTs. Anyway, typically, here's what you're going to have up to a 600, 200 amp. That's what you do 3-phase here. You go higher, then you can have a CT cabinet with a meter, a CT cabinet with a meter. Any comments, any questions about these meters, meter socket? Who decide what type of meter, Jeff? Not me, not you, the utilities. Okay, it's good to know them, but the utilities. We talked about these guys, so I'm not going to talk again. We talked about this one, how they do the grounding. Okay, look at this, is really cool. Look how they're doing the grounding and bonding, guys. This one is a grounding electrode conductor. Can you guys see how the cabinet here, the gutter, is bonded? And then they're bonding the disconnect of right inside every disconnect have to be bonded to the gutter. So they're bringing grounding electrode conductor here, and there will be, and they're all bonded together right here. Can you guys see the grounding electrode conductor? And can you guys see the neutral here is bonded to the cabinet too? So the whole bonding is happening inside this gutter, and as well as the 3-phase. Here's how they design the system. You guys have looked at this before. They have a service coming in, 1,000 amp terminal, and they're tabbing, the cheapest way of doing it, tabbing into a gutter and feeding all these services, 6 disconnect tools grouped together. They have a generator, like we did in ours, that feeds only certain loads, not all the loads, only the elevator and elevator equipment. And you can see how they sizes them exactly like we size ours. Any comment, guys, about this riser? This is a so-called one-line diagram for the building that they have. Comments, questions? We looked at that before. Grounding and bonding. This is simple, guys. You bring the grounded conductor here, and then you bond the neutral to the ground. Can you guys see the bonding right here happening neutral to the ground? And then you bring grounding electrode conductor. This is typical at the service. If you graduate from Dunwoody and you don't know this, you might have to ask your friend Chad for a refund. Okay, so that's a typical. This is how they bond, guys. Neutral disconnect means inside the disconnect, if you can see the neutral bus in a switch gear and the ground bus are bonded together. Can you see that bonding here? Then you bring your neutral conductor here. The conduit that brings the service is also bonded. That's called supply side bonding jumper. And everything is bonded to the concrete encased electrode, to the water pipe, all these electrodes that you have in your building. Can you guys see that? So the neutral, the ground are bonded inside the cabinet. Then you take a grounding conductor to the the concrete encased electrode here, as well as the water pipe and a couple of other rods. And you can see how they're bonding around. Here's a hot water pipe is bonded. Everything metallic that has some type of electrical equipment, and they have to be bonded. Again, I don't want to open the whole bonding sizing, guys. This will be open in the spring when we talk about sizing all these systems, though we size a lot of them. Okay, here's how bonding is, guys. You have two boxes. You have an EMT metallic raceway between metal boxes. Equipment grounding conductor. If it's non-metallic here, it's a must. If it's metallic, then they have to be bonded in both sides with the right fittings. Main bonding jumper, neutral isolated from the enclosures. So here's my my main bonding jumper. If you look here, this is my main panel. Can you guys look right here? System bonding jumper, you bond right inside the transformer here. That's your separated drive system. We'll talk about this one a lot when we go into the next quarter. So here's my bonding at the 480, 277. Can you guys see that? And then I go to 288, 120. I have two options. Either I bond right through the panel here, or I can bond right through the transformer. Can you guys see the bonding here? Okay, so that's two options, a system bonding jumper. Why do we bond? Because we don't want to pick that's Jeff here standing here, grabbing on water pipe and another piece of conduit gas. And if they are not on the same potential, you could have a 480. Here's the problem. You could have, this could be sitting at 0, and this could be sitting at, let's just say, 277. And then what do you have between my friend's heart here? 277. Now that's a fatal shock. That's why we bond things together. Now when we bond them together, look at this. If these are bonded together, if this is a 277 and this is also grounded, so the circuit breaker will trip before somebody get hurt. That's what bonding the two together means. The overhead, not the underground. If it's anything in close proximity to electricity, any metallic object in close proximity to electricity must be bonded. How do you bond it? Tank. If you don't know the size, just say number 6, copper. If you don't know any size, just say number 6, copper. You will cover any type of bonding. Okay, this is bonding the conduit, guys, that brings the service. You have to also bond the conduit that brings the service into the bottom of the switch gear. Same thing, bonding the conduit that brings the service. We'll talk about these again next time. Bonding conduits, the whole bonding and grounding. The distance for what? Metal pipes, what did they say? I can't remember. The water pipe or metal pipe? Oh, how far they have to be? Oh boy, this is where the judgment is. Close proximity. I don't know, 6 feet, yeah. You know, 6 feet will be extending if you have a tank sitting there and you have a transformer right next to it. 6 feet, 10 feet, probably I will bond it. just in case something get electrocuted. A tank can have a pump next to it that could energize that tank. You bond it. So judgment, 6 to 10 feet, I would say. The last thing I want to talk about, guys, is grounding, electrode equipment grounding, or uh, ground protection. Ground protection for equipment. This is called ground protection for equipment. Here's how the ground protection for equipment, guys, is used. Number one, the voltage is 480/277 volt. It's 1,000 amp or more. That's why you use a system like this, right? Can you guys see how, if the current, the way the system goes, they look at the amps that's going in each one of them. So it's going 100 amp, 100 amp, and they're looking at the 100 amp. If you see any current that's going, the difference between them, if that's carrying a 0, then it doesn't trip. If, say, the neutral is carrying 5 amps, this means one of the phases has a ground fault. It senses the difference because it's sensing here, 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 and here. It senses that there's a difference in the system, and it will send the signal here, and that signal will, bam, open this disconnect, ground fault. That's called ground fault protection. If you've never heard of it, you've never worked on a 1,000 amp service, 480/277 or higher. You guys see the requirement for this? 1,000 amp or higher, 480/277. Not required in 28120, by the way. Why high voltage, high amps? Because high voltage, high amps are when the arc becomes a big deal. When the arc becomes a big deal. Okay. So if you can, you see, if there's a difference in the amps, as you can see, if you have a ground fault right in here, there will be difference in the amps, and bam, that will sense the difference and will trip you. Okay, so a couple of other things, bonding, guys, different ways of bonding. Talked about this, what size with these, grounding, cautions, feeders. So that's basically it in terms of what I want to go over. Any comments, any questions? Any comments, any questions? I know I talked a lot about this chapter, guys, but this is one of the most important chapters probably in the whole book. It will give you a full understanding of how the power system is put together, from the utility transformer all the way into the branch circuit. I hope before you graduate from Dunwoody, will you know how the system is put together. Also, Jeff, I know you guys know it, but it gives you different options. Defining what a service conductor is, service lateral. You got to understand these. Can't believe when we start estimating, the students will come say, Chad, what type of conduit you're going to be bringing from here to this? Why do you care about this? That's owned and operated by the utilities. You know what I mean? So you have to understand where the service point is located. Service point. Very, very big deal. Any comments, any questions? Well, thank you guys for listening to Chad. I know it was a lot of information in this chapter, but believe me, it's one of the best chapters. So please read it, go over the material. The more you know, the better you'll be, right, Aaron, my friend? So as you move in your career, Aaron, some people want you to do drafting only. You're not supposed to be a drafter only. You're supposed to design your own system. If you're going to be an estimator, project manager, you cannot, shall not, will not estimate a project if you don't understand it. Right? You think you do it right, you have to understand the system. Okay, thank you guys. I'm going to do red line today, and we'll continue. Do you guys have enough info to do the low voltage stuff? I can help you with the low voltage layout, and I would like to redline the site.
Is there a security panel that we want to use or can't plan on?